Welcome back to another video. So this is actually the last video of the full lecture, and it's about Skorohod's theorem. So last time we saw in Donska's result that we have weak convergence of random walks to Brownian motion. And today we're also going to talk about a similar thing. So we want to embed Brownian motion into a random walk, but on the same probability space. That's an important difference. That means that rather we do not have weak convergence of something against something other, where we do not even need the same probability space, but we have a probability space where we have a random walk, and in this random walk we are going to construct a Brownian motion and stop the Brownian motion by certain times and find the random walk again. And using this, we have a pretty neat comparison between random walks and Brownian motion, such that, for example, the law of the iterated logarithm, which we have dealt with 2 videos ago, can be transported to random walks also. So let's see. So you might remember that Skorohod's theorem we already had in the course in probability theory, which was the very general statement that a weak convergence result can be turned into an almost sure convergence result on an appropriate probability space. Here it's similar, but still a bit different, and that we want to construct a Brownian motion and some random walk on the same probability space, such that they are close together. Here is the result. So Sn is our random walk. And on the same probability space, I can have another Brownian motion, which is a martingale, and stopping times, such that the Brownian motion evaluated at the stopping times equals the random walk. These are independent, so the stopping times, so the waiting time to the next stopping times, they are independent. And the expectation equals the variance of the y's. Let me briefly mention that without the last thing here, it would be quite trivial, actually. Because we could say, well, T1 equals the first time that xt equals y1, and T2 would be the first time after T1 such that the increment of xt minus xt1 equals y2, and so on. Which means, well, if I have my random walk, like so, and I start my Brownian motion, I simply wait until I first hit this value. And then my Brownian motion continues until I first hit this value. The problem with this approach is, well, what's the waiting time of a Brownian motion to hit, for example, 1? We had that already. The expected waiting time, so in this case, the expectation of T1 would simply be infinite. We had that. And that's not so useful because I want the expectation of the waiting time to be as small as possible. And here I can bring it down to the variance of y1. In particular, it's finite. I want to compare the Brownian motion and the random walk. But when I have to wait such a long time, which with infinite expectation, until I can compare the two, it doesn't really help. So that would be the trivial thing, but I want to make it better, and I want to make it better such that the waiting times are smaller. And there is a trick, which is essentially the content of this lemma here. Let's assume one time step in the random walk. Expectation of y is 0, and maybe we can, without loss of generality, which we will do, y is not is 0 only with probability 0. So it can be either positive or negative. Y is either positive or negative. And we want to have the following. So y has the same distribution as this complicated thing. What is y index w comma z? So y equals w comma z is y with this probability, and is z with the probability where this here is exchanged by w. So what does it mean? So w is negative and z is positive. So wyz is either negative or positive. And it's negative with some probability and it's positive with some other probability. And, well, the wz is such that w is negative and z is positive. And assume you know these, you can have wyz by saying, well, when I know these, take the negative one with this probability and the positive one with the other probability. Then you have a full distribution, so y, you have a full y then. And this is actually distributed as my y from before. So I say I have my y. Let me just draw a distribution. Well, it's maybe not symmetric. So that's the density of my y. I say to myself, well, either pick the positive or the negative one. Maybe let's take the negative one, the w. So this is this thing here. Or maybe not. No, the y has a distribution and the z has a distribution. That's what I wanted to say. The y has a distribution here. The z has a distribution here. Maybe they also have densities. We will see. Of course, here only in the negative side, and the other one only in the positive side. Oops, sorry. That should be yellow. And the point is that, well, first picking the pair y and z, and then deciding which one of the two here to choose, gives the same density as the black one from y. Yes. So let's prove this. And the point is that we can give the distribution of w and z by using this formula here. So here mu is the distribution of y. Okay, w has to be negative, z has to be positive. And by multiplying by this thing here, let's see if we can show that the integral over all w's and all z's equals 1. So when I integrate over all w's and all z's here, I have z times this here. That is the expectation of y plus. And w is less than 0 times this thing here times, mu of dw, integrating over mu, gives the expectation of y minus, which must be the same. So dividing by c gives me a 1. Because it just integrated everything out. Right, because it comes with a plus here, yes. So, yeah. Yes. So this here integrates to 1, so it's a probability distribution. And I can do the following trick. C times the expectation of f of y. Y can be positive or negative. It's, well, okay, f of 0 must be 0 here in this computation. C is both expectation of y plus and expectation of y minus. I can integrate this here on the set y is bigger than 0. Then I have this, or integrate it on y is less than 0. Then I have that y is minus y minus. So I have this thing here. I expand this here by taking independent mu's, mu for this, mu for this, mu for this, mu for this. Of course, here I have z times f of w. W is less than 0. And then y plus here is the z here. It must be positive. So z times f of w is the first thing here. And y minus is the absolute value of w. And f of z is this thing here. So I have this. And I can also write it like this. And let me see if that works. If I go from the last line to the second to last line, y index w comma z equals w with this probability. Okay, I'm multiplying the z plus absolute value of w to the other side. Then get exactly this z here. And the same holds for the w times f of z. Yeah, so bringing this to the other side, I have w divided by z plus absolute value of w times f of z. So it works, so that's true here. And now I have shown that this here equals this. I can bring the c to the other side. And I've shown that the expectation of f of y equals the expectation of f of y w comma z, where w comma z has this distribution here, 1 over z, z plus w, and this thing here, which is exactly this. And I have shown everything because I've shown that the expectation of all measurable functions with f of 0 equals 0 are the same for these two random variables. Yeah, okay. What I should write probably is that the right-hand side equals c times the expectation of f of y capital W comma z. Because how do you evaluate this? First evaluate w and z, and then you integrate this thing here. And that's exactly what's written down here. Okay, so we have this. then let's go to Brownian motion. Wz as above, which means it has this distribution. X is an independent Brownian motion. Then Tw, Z is a stopping time. So in Brownian motion, it's independent. So first we evaluate W, Z. And then we have the stopping time. And then the point is that X evaluated at the stopping time has the same distribution as Y. And the expected waiting time is finite, which is the variance of Y. So this here is, of course, the variance of Y. Proof. Okay, it's actually not very hard. We only have to put everything together. X is a Brownian motion. It's a martingale. So a stopped martingale is also a martingale. So X stopped at Twz is a martingale, which converges in L1 because it's bounded. It's bounded from below by W and bounded from above by Z against X Twz. So the expectation is 0 on the one hand. Well, and there are just two cases. X at the stopping time can be W or Z. And the probability that it is W, well, it's 1 minus the probability that it's Z. And you can solve this for the probability that it's W. And you get this thing here, which is, as you might remember, exactly this thing here. So X at Tw, Z and I made the mistake here that the W's and Z's all have to be capital, which are the random variables which are distributed as Wz from above. And I'm conditioning everything here on W and Z. And then I have this thing here. And then I can conclude, or maybe I wouldn't have needed this at all up to here, and maybe that was okay. The only thing I need is that I have the random things here. Tw, Z, so that's distributed as Y index W, Z, as from the last slide, and that's distributed as W, as Y, sorry. So, I have already that X, the Brownian motion, evaluated at the stopping time, has the same distribution as Y. Let's compute also the expectation of the waiting time. Okay, I condition on W and Z. Okay, I have monotone convergence, Twz minimum t goes to infinity. And we know that this random, so the martingale x square minus, so xt square minus t is also martingale, that's what you know. It has expectation 0, which means that this expectation here equals this expectation. And this expectation here, okay, expectation of conditional expectation equals expectation. And that's the expectation of y square, which is, as above, the variance of y. And now we can put everything together for Skorohod's result. I showed it already at the beginning, and all we have to do is iteratively do all this. W1, Z1, I need, in order to embed Y1, W2, Z2, I need to embed Y2, and so on. And I just have to restart my Brownian motion over and over again. So T1, T2, and so on are the stopping times of the increments here, either W1, Z1, or W2, Z2, and so on. And then I'm just doing that over and over again. And by the time homogeneity of both the random walk and the Brownian motion, I get my Skorohod's theorem. And here is an application, or two applications essentially. And here it's really important that the waiting times are not too long. And this corollary tells me that on the one hand side I have the random walk at time Sn and divide by square root of n. On the other hand, I have my Brownian motion. Okay, xs is a Brownian motion, xsn divided by square root of n is also a Brownian motion, but scale a bit differently. But these two things here, they converge against each other in the supremum norm, such that paths of my random walk and of my Brownian motion almost look the same. Okay, they're, of course, at some points they're exactly the same if I have the stopping times here, but the point is that I can exchange the stopping times by the fixed times, which means that the stopping times are almost the fixed times, which is not that surprising because the stopping times here, they have a finite expectation, which means that the expectation of Tn divided by n converges to the it means that 1 over n Tn converges to the expectation of T1, which is 1 in this case because I'm assuming variance of y1 equals 1. So it would be variance of y1, but that's 1. So that means that Tn is about n. That's the reason why I can use the Brownian motion at time Sn. Okay, and that's very nice because using this I can translate properties of my Brownian motion to the random walks. For example, the law of the iterated logarithm. And that's it. You can also read it in the manuscript. So Sn divided by squared n 2n log n equals also 1, as we also had for the Brownian motion. Okay, and that was it with this lecture on stochastic processes. And I hope to see you soon again. Bye.